Okay, I believe I'm live now. Now, if you can hear me, please type in the chat. What I'm going to do is I might actually leave that. Yeah, that should be fine. Okay, so if you can hear me, just say in the chat that you can hear me. What I need is that anyone that's new to this, there is a chat window in the YouTube. Please use it. This is basically how we'll communicate, and communication from me really helps. Okay, so in this hub session, I want to start off with some revision of bitwise operators, just because I've seen a lot of mistakes already, and a lot of people making mistakes with this in the assignment. And I think this is a big area of confusion. Now, with this, however, there is another complexity, which is handling your variables and arrays. But I'm going to just look at simple cases so that we get across the point of bitwise. So we'll do that to start off with, if that sounds good. And then we'll go from there. So, all right. I've got a pen color. What color should we choose? Let's go red. All right. So we know right now that each variable for an integer type, we're not going to worry about floating point types in terms of what it looks like in memory, and you don't need to know that for the exam, but we do care about integer types. So in the chat, can you list as many integer types as you can think of? So just list them, and we'll keep going. While you do that, I might copy and paste this. Where is... Delete that. I'll put that in a second. Alright, so that should be copied across. I don't need that anymore. Okay, so integer types, we have car, we have long, we have short, we have int, we have long, we have a whole heap of this. Now, these follow the same rule as in mathematics. So these are integer types. Okay. We also have unsigned. Now, in computer science, and we consider these as integers, even though they're natural numbers. Now, we also in computer science consider 0 as a natural number. So that's something also to kind of remember. But it follows the same principle as mathematics. Okay. Does that make sense? Okay. So we know that these numbers are just whole numbers that can be positive or negative, negative, or 0, and natural numbers are 0 or positive. I don't know why I put the positive and negative not way around. Okay. You will see in mathematics that natural numbers don't include 0, but in computer science it does. Okay. Now, but we consider these as integer types. Okay. But if we want to compare it to mathematics, because it might be more comfortable for some people, they're all integers. Now, the other difference from mathematics is that we have storage types. So depending on the storage type, it depends on how big of a number we can hold. Now, I'm going to ignore the longs just because I can't be bothered writing out much, but I'm going to look at car short and short. Okay. For now. So a car is 1 byte, and a short is 2 bytes. Okay. And an unsigned car and an unsigned short is also 2 bytes. Now, when we look at a car and we look at a short, if I counted, I'm just going to make that up. Whatever, it's close enough. Now, if it's a signed number, this top most significant bit is the sign bit. Okay. And this tells us if the number is negative or positive. However, when it's negative, these are stored in twos complement form. Now, this is in the lecture notes. I'm not going to go through it now. It's not expected that you're able to do it offhand, but you should understand that this isn't stored like you'd think it is. Okay? If we have time a little later, I'll go through it. But I want to go through the bitwise stuff first because it's a bit more important. So generally with bitwise, because we don't really care about the sign bit unless we're doing bitwise mathematics, which in this case we're not. We're just using the bits as flags. We'll tend to stick to unsigned because it means we get the full 8 bytes and we don't have to worry about that sign bit and the two's complement. Okay? And the two's complement can ruin all your flags. Okay? Because it'll flip everything. Yeah, that looks good enough. Okay, so with unsigned, all of these are just numbers. There's no sign bit. Okay. Cool. Cool, cool, cool. Now, we know cars are 8-bit, shorts are 16-bit. So in memory, they can store numbers, okay? And how these numbers are stored, they're stored in base 2, so binary. 2, 3, 4. And so each one of these bits, 1, 2, 3, 4, 4, 2, 3, 4. So each one of these bits can be 0 or a 1. Okay, and so when we put these together, they can represent different things depending on how we read this information. So this could be read as an ASCII character. Oops, I spelled that wrong. ASCII character. It could be read as a decimal number. It could be read as an octal number. It could be read as a hex number. It could be read as a binary number. And there's other things that it could be read as. It could be read as flags. And this is the one we're concerned about. Okay, so there's 8 bits of information here. And depending on how we read it, it has a different meaning. Okay? And this is a really important thing to remember. And this car here confuses a lot of people because they see car and they go, well, obviously, we store the letter A in memory. Memory doesn't work like that. Unfortunately, I don't think many of you will do digital electronics, but all your memory is 1s and 0s. We can't actually go into memory and store A. Okay? So we need something to represent A. And that's where the ASCII format comes, or the more commonly used Unicode, but we don't have that in C. Okay? Okay? Does that make sense? And it's just conceptually really important that you understand that how we read that information changes its meaning. Or do we need an example? Just let me know if you need an example or not. Or if you understand. Just say yes or no. So if you're watching, I know there's quite a few people watching right now, so please use the chat. I know there's a slight delay, but okay, so let's do a very quick example. All right, so I'm going to grab a number. I just need to find out what number I want. All right, I'm going to choose. That's a good number. Okay, all right. Okay, so I'm going to look at all of these. Okay, now the flags ones won't make much sense in this example, but we can have a look at it. So I'm going to put in memory 0, 1, 0, 0, 1, 1, 0, 1. Okay. Now, if I look at my ASCII table, and actually I won't start with ASCII because it'll make it easier. So if I convert this number into decimal, I get the number 77 in base 10. If I convert this number into octal, I get 115 in base 8. If I convert this number into hexadecimal, I get 4D in base 16. If I convert this into binary, I get 01001101 in base 2. And these are just number systems. So these numbers are equivalent, it just has a different base. Now, in high school and primary school, you've been used to using base 10, but there are basically every integer can be a base. So you can have base 256 and so on. And that can be very, very handy for storing large amounts of data. And we have the ASCII character, which is M. Okay, so how we read this has different meaning depending on how we read it. Now, the flags could also mean something, but if we're using flags, we have to associate meaning to each one of these. Okay, so I'm going to call this error 0, error 1, error 2, error 3, error 4, error 5, error 6, and error 7. So in this case, given this definition, the system has error 0, 2, 3, and 6. Okay? So you can see in this small amount of information, we can actually represent quite a lot, and we don't need to change the memory to make it represent something. It's how we read it. And this is also important with when we use our functions, we have the F, which stands for formatted. And so the formatting is taking this and turning it into a formatted form. Okay? Does that make sense? Now, some of these conversions are fairly confusing, but there is one conversion that you're expected to know for the exam, and this is this one. Okay? And it goes the other way as well. So going from binary to hex and hex to binary. And pretty much every second week I've done examples of this on the help sessions to ensure that you can do it fairly quickly. Okay, so I'll give you a second. Does that make sense? Just say yes, no, maybe, on board, etc. And I'm just going to check the email. So if you just joined us, please use the YouTube chat. This is a really important factor for me to hang around and do this. Yes. So someone asked about converting between hex and binary. Yes, I can, but I'll do it later. So remind me a little bit later, because I think most people who have been watching regularly have seen too many. So I want to not bore everyone with that. So we'll do it a little bit later. I want to get onto the binary stuff first. So I'm going to get rid of all this crap. Okay, just remind me. Oh, damn it. Okay, so we've seen that if we have an unsigned car, we can associate each of these bits to mean something. And in this case, each one's an error number. Now, we have, in this case, 8 flags. If we used an unsigned short, well, the association's with us. Now, we can use macros to ensure that we are always assigning the same bits to the same bits. There is no relationship there otherwise. You can actually do some interesting stuff with structs, but we don't cover that in this subject. Cool. So in this case, we'd have 16 flags instead, and if we used a int, we'd have 32. If we used a long, we'd have 64, and so on. Okay? So depending on the type, the more flags we can have. Now, it's not always the case that we'll use all the flags, and it may be the case that you may have 2-bit or 3-bit flags. And even though you guys won't do embedded anymore, you may see things where you've got 2 bits for a 2-bit flag that has 4 values. Okay, and you can do things like that as well, and get fairly complex in terms of your memory management. But we're not going to go down that rabbit hole. All right. So I showed you a couple of week 3, I think it was. We looked at this. So this was simple operations for setting, clearing, toggling, and testing. Now, this did remove some of the understanding of bitwise operations because we have the OR, the AND, the NOT, the XOR, and the bitwise AND here. And we just converted that into a simple little bit of code that could be used to do an operation. Now, it doesn't mean that that's actually a C operator. It's just that it's a nice way to put it to do a simple operation. You still need to understand what's happening before that, and we've broken them up in the past. But we don't have time to cover all of them right now, because it would take probably an hour to go over all of these. But we did go over it in the previous videos. So if you look around week 4, I think it is, you should find the video there about breaking these up into its actual components. So we have this example here, and so I'm going to create car A. Okay. Now, if I set car A to 0, 0 in binary, so let's say 0 in base 10, 0 in binary is just all zeros. 0 in hex is just all zeros. Here, 0 in, you should understand what they mean if you do break them up into their components for the exam. Well, this is what I mean. So when we were doing week 4, in the lecture notes, Somnath goes over this, and in one of the help sessions in week 4, I went through every single one of these in detail. Okay, so if we have time later, but it'll probably take about an hour to cover. So let's do this first and make sure we can get this working, and then we'll have a look at this. And yes, you should be able to understand what each one of these operators mean by themselves as well. Okay, so in base 8, it's also zeros. So if we initialize to 0, it just basically gives us a blank box of zeros in memory. Okay, so we've got a bunch of zeros for our A. Okay. Now, we can do a bunch of different operations here. Now, I'm treating it as these error flags. And so if I wanted to indicate that error 0 is active, I would just go A, binary OR equals as a compound statement, 1 shifted to 0. Okay? And that would indicate that error 1 has been set. If I wanted to clear that, I would go and equal not 1 shifted 0. So now it becomes a 0. If I wanted to toggle one of these, I could go A XOR 1 shifted Let's do a different bit. So I'm going to do error 1 now. I'm going to set this to 1. And this will set this one to a 1. Okay? And if I want to test if 1's set, then I would go if A and 1 shifted. Let's say I want to test if this one's a 1, 1. Okay? And that will test if it's set. Printf error 1. Okay? Yes, so toggling goes from 0 to 1 and 1 to 0. Okay? And if we do a full XOR operation, we should see the whole thing flip. All right, so this is how we test. Now, if we want to test if it's not set, then we go not A and 1 to 1. And we can just say printf not error 1. Okay. And that pretty much gives us all the operations we need for the assignment. So it's set, we've got clear, we've got toggle, we've got test if 1, and we've got test if 0. Okay. We're getting there. Calm down, calm down, calm down. All right. Now, obviously, these here are kind of confusing. We could use a variable. So I could go error, so I could go int error 1, well, error 0 equals 0. Int error 1 equals 1. And replace these with variables. Now this would work, but it would be highly, highly inefficient because we're basically just setting constants to a variable. So what we do instead, because we know that the preprocessor will change these variables at precompile time, and it will actually just replace these with its natural constant values, we can use macros. Now, is this going to all come down with me? Yes, it is. Damn it. So we'll move that up a bit. So what we can do is now we can introduce macros. So we go hash define. Now these should be in capital. Error 0 is bit 0. Hash define. Error 1 is a 1. Hash define. Error 2 is a 2. Now that means that we end up with what I'm going to actually do. Do that. I don't really care if it's not all of it. Ah. Right. So that means that we change this here from a 0, and now we write error 0 here. Okay. Here we write error 0. Here we write error 1. Here we write error 1. Here we write error 1. Okay, so we end up with a whole heap of macros there. Now at precompile time, it will change to this anyway, but this is readable, and if we need to change the bits around, we can. It doesn't affect the efficiency at all. It will still be as fast if you do it this way or this way, but this way is readable and modifiable. They are both exactly the same in terms of C code though. because of the precompiler. Okay, so when we precompile, which is before the compiler, which gets rid of all our macros, it's going to replace with these values that are here. Okay, so it's just important to note that it doesn't change the efficiency, but it gives some meaningful name, making it more readable, and it also makes it modifiable. So if I need to go, okay, not anymore, error 0 is not 0 anymore, it's going to be bit 3. I can change it all through my code very quickly. Okay, does that make sense so far? So I might just do another quick example. Now, your variable is stuck in a struct. It doesn't change anything. So let's do struct dog. And in that dog, I've got its dog type, which is going to be a car. Okay. So with that, I'm going to define some stuff. And this is going to be a flag byte. Okay. So I'm going to define, let's say, if it's female, it's a 1. Bit 0 is set, else it's a male. Hash define. If it's, I don't know. If it's old, then that's bit 1. If it's big, then that'll be bit 2. Okay, so now I've got this inside here. Now yours is an array. Here it's just a standard variable, so yours is a little bit more complex, but still follows the same principle. So I'm going to create this dog called doggy, and from that I'm just going to go doggy dot dog type or equal. Now what I might do beforehand, just because it's uninitialized, is I'll set it all to 0. Now there is obviously 8 bits here. The top 5 I'm ignoring, I don't care, but I still want to set these to 0, and I want to set these ones to 0 so I know that there's a 0 in them. So I just set everything to 0 to start off with. Then I go doggy dot dog type or equals 1 shifted female. And then I go doggy dot dog type or equals 1 to big. And then I'm going to do if statement, and I'll go doggy dot dog type and I will do an and I'll go 1 female. So I will go printf dog is female, else printf dog is male. Okay, So here I'm using a struct. It doesn't make a difference. Struct just uses the normal type. It just is able to store more information. So yeah, does that example make sense? So what would be printed in this case? Yeah. So you've got an array of structs. So the only difference here, if we had an array, would be that there'd be a brace and then the dog type. If it was a single dimension array, and if it's two-dimensional, it'd just be that, with whatever one you're looking at, dog type. Again, that's the only difference that would change here in this case. Okay. Does that make sense? So we know how to do all the tests now. We've got an example: set, clear, toggle, test if 1, test if 0. So if I want to test if it's not female, I can just put a not there and put a bracket around the whole thing. Okay. Or I can just compare if it equals 0. Okay, so given that, I might just quickly go back to the assignment. I want to recap something really quickly, because I've already been over this, but if we have a 4x4 board, then the board size is going to be, my lines aren't very straight. What I should do is actually go straight. Move the mouse. I want it. All right. So I want it. 2, 3, 6. So let's get this up. Cool. All right. So if I have a 4x4 board in the assignment, then remember when we're mallocating the memory, we get the +2 for both the, so this is the columns, and this is the rows. Okay. And we have 0, 1, 2, 3, 4, 5. And we have 0, 1, 2, 3, 4, 5. Okay. So the board size is 4x4 when they put it in, but our board size on the programmer's side is actually a 6x6 because we add that +2. Okay. Now, each one of these spots is a struct location. And a struct location has two things in it. It has a value and it has a status byte. And this status byte has 3 bits of information. So a struct location, every location includes 4 bits of information. Okay? So every one of these includes 4 bits of information. All right? So I'm going to write this like this. It's a little bit of a weird notation, but I think it helps to understand what's happening. Okay, so you can imagine the board as being basically every spot contains 4 bits of information. It includes its value and its status byte, which contains 3 bits of information inside that. Okay? Now, let's just make some definitions. So this is the value, this is if it's a mine, this is if it's a flag, and this is if it's revealed. Okay? Now, you can do this however you like. I'm just making this up. So we know we go through the board, and this border section isn't part of the playing game. So the value for all of these, and I should choose a number, is all zeros. Okay? And we do that when we do our initialized board, I think. We also, first thing we set inside here, around the outside also, is that these are revealed. Okay, so we've got revealed, 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 and revealed. Okay. Now, in this inner bit, we set X amount of mines randomly. So I'm going to set 4 mines randomly. Okay, and that number is valid because we can only have, we have to have less than 16. So choose another color. That's another color. Let's get that color. Which one I do for mines? So I'm going to set 4 mines randomly. Okay. Now we go through and we change our values in these ones. We've already done the values for the outer ones. So the value here is 1. The value here is 2. The value here is 1. The value here is 0. The value here is 3. The value here is 2. The value here is 1. The value here is 1. The value here is 1. The value here is 2. The value here is 1. The value here is 1. The value here is 1, 1, 1, and 1. Okay? So we can see that the mines also have a value. They don't really need to. It doesn't really make a difference if they do or don't. But they're just counting around the outside as well. We could optimize this so that it doesn't calculate a value, but let's just keep it simple for now. All right. Okay. Let's play a game of Minesweeper. What I do. Well, let's have a look at this first, and then we'll play a game of Minesweeper for fun. All right. So basically, what these values represent. Now, don't worry too much about the ones with mines because they don't really mean much when they have a mine. But let's have a look at this one. Okay, where I got that 2 from. So basically what I do is I count the number of mines in the, I'm running out of colors. I wish there was more colors in the spectrum. So this has, actually I'm going to move to another layer as well. So this has 8 surrounding spots, all right? So we're looking at this one, and we're going to look at the 8 surrounding spots. And we're going to check each one and count how many mines it has. And this was covered in the other video that's up on LMS next to the assignment. So we count this one, it has 0 mines. So we have 0, plus 0 mines, plus 0 mines, plus 0 mines. There is 1 mine here, so plus 1. There is 0 mines here. There is 1 mine here, so plus 1. And there's 0 mines here. Now, we can check if there's a mine in each one of these spots using our AND and an if statement. There is actually a better way to do that, but I'm just expecting most people to use if statements, so I might show you that after the assignment's submitted, if anyone cares. All right, so we add these up and we get 2. And it just means that there's 2 mines in the 8 that surround it. Okay, so if we go to a game of Minesweeper, I'm going to make this bigger. Yep, there we go. So this is a game of Minesweeper. If I look at this 1 right here, it means that in all these 8 spots, there is 1 mine. Now I know if I click on this, that this has to be a mine because all the other ones are revealed. So if I click on this, there's a mine there. There's definitely a mine. Now, the game of this is basically that this is a 2, so I don't know which 2 out of these 3 is a mine. Okay, so I know out of these 3, 2 are a mine. So I use this information and I know that there's 1 here. And so I flag this, and that's why you've got the flag bit. Now I can look at this and go, okay, there's 1, and that's, sorry, there's 1 mine in these 8, but because this is already flagged, I know that this one isn't a mine. Then I can look at this, and in this 8 there's 2. I know there's 1 here, so the other one by is also a mine. Same here, I can work out that's a mine, and so on. Okay, does that make sense? Now, the uncover zeros, now we're not doing the traditional uncover zeros, we're just doing diagonals as well, but it doesn't really matter. But you'll notice when I click some places, we get this big uncovering. Now, all of these empty ones are zeros, okay? So there's 0 mines surrounding it. And so what it does is that it clears that big spot. Now this is the same in our examples as well. So if you have a look on LMS, wherever LMS is, how is LMS? I did have LMS. I think I closed LMS. Damn it. So if we have a look on LMS and go to example outputs, we can, why doesn't it come up as a pop-up? That's really annoying. So you can have a look at the game and you'll notice that Come on. When we click in certain places, it'll open up the whole board. It's probably hard to see on that screen as well. All right. Cool. All right. So what we're going to do now is I'm going to have a quick break, and then we'll go over conversion from hex to binary quickly, and then I'm open for suggestions, or I will go on to something that's important for the exam. All right. So I'm just going to have a quick break. It would help if I unmuted myself, because everyone wants to hear my voice. All right. So let's quickly go over conversion from binary to hex and hex to binary. Now, the easiest way to do this quickly is when you get into the exam, you quickly draw up the table from 0 to 15. So you go 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0, 0, 1, 0, 1, 0, 1, 1, 0, 0, 1, 1, 1, 1, 0, 0, 0, 1, 0, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 1, 1, 1, 0, 0, 1, 1, 0, 1, 1, 1, 1, 0, 1, 1, 1, 1. Now, it may have seemed like I've been pulling these numbers out. So there is a pattern here. And if we look at decimal, it's the same pattern. So if we go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1, 2, 3, 4, 5, and so on, we end up with different units. Okay. Now, we should understand that we are adding numbers. Ideally, you shouldn't need the table, but at this stage, it's okay. But when we have 0, the next number in line is a 1, so 0 plus 1. Now, we carry the 1 when we add a 1 to this, so we get a 1 and a 0. When we add a 1 to this, we get 1 and 1. When we add a 1 to this, we carry the 1 until we get 1, 0, 0. Now, there is a pattern. However, be aware that you should understand what this means before you just use the pattern. So you'll notice that the pattern is 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 4 zeros, 4 ones, 4 zeros, 4 ones, 8 zeros, and 8 ones. And it goes the same with decimal if we draw it all up, but we'd have a lot bigger table because we'd be going from 0 to 9. Okay? So make sure that you understand that it is adding up in in twos, sorry. We're in base 2. We're not, base 10 is counting up by 10s. Now, all we can do here now is count up by base 16. Okay. So base 16, we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. And when we add 1 to this, we carry because there's no more room, and so we end up with 1, 0. And then we end up with 1, 1, 1, 2, and so on. Okay, so it follows the same rule as decimal, except for this is base 16, and this is base 2. So in base 10, each unit can go from 0 to 9. In base 2, each unit can go from 0 to 1. And in base 16, it can go from 0 to F, which is 15 in decimal. Okay, and in base 8, it can go from 0 to 7. Okay, so it's just knowing when to carry, depending on the base. So we know in base 10, when we reach the 9, if I add a 1 to 9, I know I have to carry, and I get a 1, 0. Okay, where in base 8, if I add a 1 to 7, then I carry. Okay, does that make sense? Most students are fairly new to bases because they've only used one base before. So that's probably the simplest way to explain it without going into too much detail. Now, it can get really confusing if you start doing multiplication and stuff like that with different bases because you're not used to it, but they all follow the same rules. Okay, sort of. So what's confusing? Let's sort this out. So well, let's just have a look. So decimal is just a common base because everything's around deci, which is 10. But for example, octal, it's all around 8. Binary, it's around 2 because of bi, and so on. So hex numbers over 15. So let's look at the difference between decimal and hexadecimal. So I've got 0, 1, 2, 3, 4, 5, 6, 7, 8. So let's do a couple at the same time. So we'll do base 10, 16, and 8. So this is going to be base 8. This is going to be base 10. This is going to be base 16. So base 8, we go 0, 1, 2, 3, 4, 5, 6, 7. When we add 1 to 7, we have to carry because we can't go above that base, so we get 1, 0. In decimal, we get to, can't even count. We get to 9, and we can't keep counting because we've only got 10 digits because we're in base 10, so we go 1, 0. Now, in base 8, if we continue, we get 1, 1. I should line these up so they're aligned. That should be there. 1, 2. And so if I keep counting this up, we get 1, 3, 1, 4, 1, 5, 1, 6, 1, 7. I can't go beyond 7, so I get 2, 0. And my layers behind something. Okay, where in decimal, this would be 11, 12, 13, 14, 15, 16. So 16 in decimal is 2, 0 in base 8. Okay. Now in base 16, we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. Now you'll notice here in base 10, there's 10 here in base 8, there's 8 here in base 16, there's 16 here. And so we can't add anything more, so we carry and we get a 1, 0. And we go 1, 1, 1, 2, 1, 3, 1, 4, 5, 1, 6, 1, 7, 1, 8, 1, 9, 1, A, 1, B, 1, C, 1, D, 1, E, 1, F, and carry, we get 1, 2, 0, and then 2, 1, 2, 2, and so on. Does that make sense? Cool. Cool, cool, cool. Yeah, it's a bit weird to first get your head around, but once you actually get it, it's actually fairly simple until you start using it with maths. It just gets annoying. But with computer science and engineering, hexadecimal can be quite confusing. I mean, quite not quite confusing, quite helpful, sorry. It's better than base 10. Like, I rarely use base 10 when doing stuff with computers. And you'll see why in a second. So if I had a big block of memory, okay, and let's say it's a 64-bit number, okay. Now, if I wanted to write this out as a binary number, this would take a while because I have to write 64 bits. So I'm actually going to do that. I'm going to write a big long number. So I'm going to write long A is equal to 0B 1111 0110 1010 1110 0000 1100 1000 So we should have 8 16th. That gives us 32. 16, 24, 32. So we need to keep going to 64-bit number. 1 0 0 1 1 1 1 1. Then we go 1 0 0 1. And I've lost track of that. But 0 0 1 1. 0 0 0 1 1 1 0 0 0 0 1 1 1 1 1 1. Okay, so I've got this massive binary number here. Now, converting this to decimal can be rather difficult and annoying. Okay, and it doesn't really mean much in decimal when I'm talking about memory because the conversion is very cumbersome. But if I can convert this to hexadecimal, it's actually quite useful because I can represent this number quite quickly. So how we do this is we break our number up into fours, starting from the very end and going up. So the first one, we have 4 ones. So we can look at our table and we know 4 ones is an F. We then look at the next 4 digits and we have 0, 0, 0, 1. We can look at our table and that should give us a 1. We then look at the next 4 digits and we have 1, 1, 0, 0. And if we look at our table, that should give us C. And so we've done them 3. Then we have 1 again. Then we have 3. We have 9. Then we have F. Then we have 9. We need a little bit more room. Now I've lost where I'm at. We have 1. We have 8. We have C. We have 0. We have E. We have 10, which is A. We have here 6, sorry. We have F. So we have A equals 0x this. And we can see that this divided this by 4. Okay, and this is still a fairly big number, but you can see that this is a lot better way to represent this number than in binary. And we can quickly convert between these, and we can kind of read this and know what's happening in binary. Now this is a long, so this is quite a big number, but let's go something simpler. Okay, so I'm going to do a couple of simpler examples. But you can see yes, there is a reason I'm going from right to left, and it's purely because when I'm converting, so if I have 0, 1, 1, 0, 0, 0, 1, now if I convert from this way, you'll notice that I run out of bits. Okay, so there's not 4 bits here. Where if I convert from this way, I can always add a 0 to the front. Okay, and this follows decimal as well. So if I have the number 901, I can always add zeros and it's still 901. Okay, it's the same in binary. If I have 0, 1, 1, 0, 0, 0, 1, then this first part is 0, 0, 0, 1, and I can just add another 0 here to make it a group of 4, because I can always add zeros in front of a number. Okay, so here in hex I get 31. Does that make sense? And that's in hex. That's space 16. It's space 2. Cool. Cool, cool, cool. All right. Cool, 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 cool. All right. Have we got any questions about other questions about the assignment that you want to ask? So we'll give you an opportunity now. I don't know if that was a big delay or that was an answer to the question. Example of how to uncover. So well, the uncover zeros, the easiest way is recursion. Okay. Okay. So recursion is a function that calls itself and it needs an exit point. Okay. So your recursive function is going to be a tree, which might sound weird, but you start with one function. So I'll have a look at the board. What I might do is just create a new file. Now, the recursion part is meant to be difficult, so I'm not going to give away too much. And there's already 3 people that have got it. So I need to be careful with what I give away. Why is the code? I'll go away. Can't bother doing it that way. Do it this way. Every way. Sideways. Give me a second. I'll do it another way. Looks like a pretty good grid. Okay, so I've got a grid here. I don't know how big it is. Probably help. So we've got 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay. And the game area is from here to here to here, and I did a mistake. Okay, that's better. So the game area is from here to, I can't do all that. So from here to here, here. Okay, so that's the outside region. The inside region is the game. Now, what I'm going to do is just set a couple of mines. So this one's a mine, 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 this one's a mine. And I'm actually going to block half the board, so I don't have to worry about it. So this one's a mine, this one's a mine, this one's a mine, this one's a mine, this one's a mine. Okay. So we have a 2, we have a 3, we have a 4, sorry. We have a 4, we have 2, we have, keep doing that, we have a 4, we have a 3, we have a 3, we have a 3, 3, 3, we have 1, 1, 2, we have a 1, no, we have a 2 there, sorry. We have a 1, 1, 1, this one has a 2, we have a 1, 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 we have a 1. In here we have, what do we have? We have, this one has a 1, 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 and this one has a 1. I think I've got, that one also has a 1. Okay, so the rest here, so all the rest here are zeros. Okay? Yeah, that one doesn't have it. So we've got 0 here, 0 here, 0 here, 0 here. Now our zeros are going diagonally, but we don't really care. So what we want to do is be able to pick any spot on this board. Now, do not attempt this till everything is working, and make sure you make a copy. Okay? Because this is conceptually the hardest part, and this is if you want to get above a 90. Okay? The scoring's set so that you can't get above a 90 unless you do this. And it is possible, 3 people have already done it. So I pick this one here. Okay? So I pick this one here, and this becomes revealed. Okay? And I call my, because this is a 0, I call the uncover 0 function. Now I'm going to do this recursively. So what this recursive function does, now remember that all these outer ones are revealed as well. The recursive function is going to be called, and it's going to do basically what we did with the count lines, except for it's going to call a function. So it'll first look at this one and go, it's already revealed, so I'll ignore that. Then it'll look at this one and go, it's already revealed, so I'll ignore that. Then it goes to this one and go, it's already revealed, so I'll ignore that. Then it gets to this one. Okay? So now what it does is it calls the function on here. Okay? So now the function, so this function is still running, but another function inside that, which is the same function, has been called for this location. And this one's going to do the same thing. So it's going to check here. No, that's already revealed. It's going to check here. No, that's already revealed. It's going to check here. No, that's already revealed. And then it checks here. And this is a 0. So it calls that function. Now this one here is going to check this location, check this location, check this location, and then go, oh, there's another 0. So it's probably a big set, so it's going to take a little while. And in here, in this function, so we've got, at this stage, 4 function calls on the stack that are all the same function. So we've got 4 calls to uncover zeros. So uncover zeros has been called and hasn't been returned 4 times now. Okay. So we get here, it checks this one, checks this one, checks this one, checks this one. Okay, that one obviously is not a 0 either. I mean, is a 0 as well. So now we've got 5 calls on the stack. And this one here checks this one, checks this one, checks this one, checks this one, checks this one. Oh, one thing I forgot to mention is it set that to revealed as well as it goes. So they're all revealed. Okay, that's important because if we don't do that, we'll end up in an infinite loop. So it checks all the ones around it, and then it gets here and goes, that's a 0. Okay, so we end up with calling this one. And we get a 0. That's revealed. Then this one is going to check this location, but that's already revealed. That's already revealed. So you can see it's checking all the locations around it. Checks this one, that's already revealed. Checks this one, it's already revealed. Checks this one. So you can see we're branching. Now this isn't a very exciting branching case. There's more exciting ones. So we've got quite a bit on the stack now. And this one's going to do the same thing. It's going to go around, checks that one, checks that one, checks that one. Okay. That one's not revealed, so we're calling the function again. So we get revealed 0. Now I probably should have done another line somewhere, because this is going to go on forever otherwise. So what I'm going to do is I'm going to put a mine right here. Okay, and that changes some of these. So that's now a 1, that's now a 1, that's now a 1. This one here's a 2. And that one here's a 2 as well. Yeah, I'm just making it a little bit quicker. All right. So now this one is going to go around. Now, oh, I made a mistake as well. We started at the top left-hand corner. So this one, yeah, that's all right. This one should call here because it starts at the top left-hand corner. So this one's calling that one. Okay. So we've got heaps on the stack now. And this is why recursion's kind of dangerous, because we're going to end up with too many calls. Then this one checks this one, this one, this one, this one, this one. And then it'll check this one, which is also a 0 and now revealed. So it'll skip all these ones because they're already revealed. Then this one does the next same thing. So we end up here and we get 0 and revealed. Okay. Then this one does the same thing, so it will check all the ones that surround it, gets here, and this is 0 and revealed. This one will now check all the ones that surround it. Okay, and it'll notice, okay, I'm done. I'm returning from the function. There's no more zeros that aren't revealed around me. So that one's done. So we get back here. Now this one was only up to here. So it's going to check this one still, then this one, and then this one, and go, okay, there's no more zeros around me. So this one's done. So it will return. This one here, it was up to here, so we'll check this one, 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 and go, okay, there's no more zeros that aren't revealed around me. And so this will slowly collapse. Now, this is where the branching comes out, and you'll see this in a second. And we keep going back, and we get to this one. And we're here, and we go down here and keep checking because it needs to still check before it returns. That's a 1, that's a 1. Ooh, this one's a 0. So now we open up another root. So we end up with 0R there. And then this one's going to do the same checks. So it goes through this and goes, okay, that one's a 0 and an R. So it opens that one up. And we get 0 and an R here. And this one checks, we get a 0R here. Now this is quite an interesting situation. So this one exits because there's no more 0Rs around it. This one exits. This one continues counting, and we end up with the 1 here. This one finishes and returns. This one finishes, returns, returns, returns. So we can see that we start with this one branch, and it kind of branches out, and it could have multiple branches. So in this case, we saw 2 small branches here, and just 1 big long branch here. But the more complex, the more branches that could come out. Okay, so it could be quite a big tree. Okay, and that's what I mean by tree. Okay, so you can see how it's trying to get into all these corners. And that's how the recursion works. How do we find that? So I've given a couple of clues with recursion. I can go over another example with recursion, or the same example I did last week, but maybe a little better. I was a bit tired and a bit crappy with the explanation on my part last time. But that's basically what you're doing with the uncover zeros. So you're going to be calling the function quite a lot. And the tree gets to the end, which is called a leaf node. And once it reaches that leaf node, it will go travel back up. Okay. Does that make sense? Sort of. And that is it's actually not the best way to go about it, but it's the easiest way to go about it. It actually depends on the language as well. For some languages, that's the best way to go about it. For C, it's not the best way to go about it. So, and to actually change it from a hash to that, well, that depends on your print function. That has nothing to do with the status byte. That's just your print function. So this is if, well, this one has to do with your status byte. This one has to do with the value. So that's the value. That's the status byte. And that's the revealed bit. Yes, it will also reveal the 8 places around it. Sorry. Yeah, so they'll be revealed as well. Sorry. Good point. I missed that. So yeah, the tree actually goes further. It goes to here because it reveals these as well. But it doesn't have to actually call the function on these because it's not continuing. So it'll actually reveal from the leaf node. So it can reveal from here. So as it's going, it can reveal. So if it's not a 0, it just reveals it. If it's not a 0, it reveals it. If it's not a 0, it reveals it. Good point. All right. So one thing that some students have been doing, which is really clever, is that when you start developing, you're going to print everything out as hashes. Now, it's a good idea to just set in a debug everything to revealed, because then you'll see the whole game. Now, obviously, you can't play the game, but if you set them all to revealed, you won't get the hashes. You should get all the values instead, and the mines and everything, so you can test your board out. And that's purely just by debugging. All right, have we got any more questions? Handling the game variables in the function. I don't understand your question. Oh, I know what you mean. Okay. So I need to be careful here that I don't give too much information away, because I need to make sure that I'm still testing your understanding and that you're not just implementing what I'm saying. So the game variables, yeah, so the game variables are blah, blah, blah. The width, the height, the mines flagged, and the flags. Now these two you can't change because the width and height never changes. You can't change the number of mines either. So it's only the mines flagged and the flags. So whenever there's a flag placed on the board, this goes up by 1. Whenever a flag gets removed, this goes down by 1. Okay. The mines flagged whenever a flag goes on the board, and it is over a mine, we add 1. And whenever a flag that is over a mine is removed, we remove 1. So let's do a quick example. Bump, 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 bump. Why can't I draw straight lines now? No, maybe not. I spoke too soon. Okay, so this is my game board. Okay, so in this, I'm going to set up a couple of mines. So let's say this is a mine, this is a mine, this is a mine, this is a mine, and this is a mine. Okay. So we've got 5 mines on the board. Okay. So in our game variables, mines, or mine, I can't remember what it's called, is 5. And that's going to stay 5. It can't change. Now, the mines flagged and flags, considering this is a new game, what should both of those be at this stage? So I open up to the chat to answer that question. Okay. Okay, so they're both 0. We'll do it in purple. Okay. If I put a flag here, sorry, put it in a different corner. So I can put both. If I put a flag here, what changes? So these variables you can test yourself. So I'm not going to, because you can test it and compare it. So you can print these out in a debug and go, oh, they don't match what's on the board. So in this case, we'll have flags as 1. Okay, because there's 1 flag, but there's none that are over a mine. Okay, so I put a flag here. What happens now? Yes. So this goes up and this goes up. So there's 2 flags, but only one of them is over a mine. Okay, so I add this flag, this flag, this flag, and this flag. What's my values now? I think we're learning more about Minesweeper than we are C code here. Nothing wrong with that. Minesweeper is a good game of logic. Okay, so we've got 6 flags, and we've got 3 that are mines flag. So these are something you can easily test with your debugging. you can check how many of these are true and then just count the number of flags either manually or by using some kind of counter. And you can just compare, are these true? Now, if I remove this flag, what happens? So we've lost one flag, so we definitely have to remove one from there. So we end up with 5. And we also lost one that was flagged, so we end up with 2. Okay. And if we remove this one and this one, what do we end up with? Cool. So I think you've got this under control. I'm gonna have a quick break. I just need to sort something out. And then we'll go over some more revision on things that might be useful for the exam and assignment. So I'm just gonna have a quick break because I'm gonna sort something out. All right, I'm back. So one thing I want to quickly cover. Why are you frozen? One thing I wanted to quickly cover was in the assignment, not in the assignment, in the last lab when I was marking it, I saw this. If some kind of check, a lot of people read check or flag or something like that. If check, printf, invalid student information. Okay, does everyone remember that? Okay. So I saw some people do a comment, and they wrote, checks if it is an error. Now, this is just terminology, and this is quite important in terms of coding. Okay. Now, what I want to ask you is this here an error? And we have to be careful about this word error. Okay. No, it's not. Okay. Our code is doing the right thing if it's invalid student information. On the system that created the marks, it would be an error. But on our system that's checking, this is valid. It's actually checking, so it's not an error. So just be careful about your terminology and errors and how you end your program early. If it's not an error, you shouldn't finish your program early. It should return 0 and get to the bottom of your code. However, if it is an error, then you should exit early because there's nothing you can do in a lot of cases unless you can recover from an error. And there are critical errors, and then there are recoverable errors. And it depends on what kind of error. At this stage, because we haven't really dealt with errors and error recovery, we just usually exit early. Okay, but just be careful of terminology. This is not an error. Okay. Yeah, something like that's fine. But just be careful of terminology. Okay. Because this is not an error. All right. It's just something I wanted to mention. Okay. Now, a lot of people use the debug inappropriately. When we're coding and we're going through it, the beauty of debugging is that we are checking both types of errors at the same time. Now, debugging is not talking to the user, it's talking to the programmer. So we can be technical, okay? Now, I have shown some people how to do multi-level debugging, but that doesn't really matter. Okay. So, however, a user message needs to be not technical, okay? Because they don't know. Now, this can be confusing because it depends on the domain as well. So, I say not technical, but if you're writing a system for, let's say, aerospace, the user information is going to be around the domain. So it's technically around aerospace, but it's not technically around the programming. Okay. Okay. So when debugging, and this leads on to development types, and there's a development type called TTD, which stands for TDD, which is called test-driven development. And we're not doing full TDD, but we're kind of doing it already. And this basically means that what I do is every time there is a condition or a calculation, I stop and compile and I check the output. Okay. So in this, I'll write int a, and then I'll do a becomes 4 plus 2. Then I'll do if def debug printf, some kind of indicator that it's not a user message. I will use my variable name, and I will usually actually give the whole equation so I know what I'm talking about. And I'll put a semicolon, and then I'll put a becomes %d, and then a new line, something along those lines, and then end if. Then what I do is compile. Okay, and what I'm checking at this stage is two things. So I'm checking for syntax errors, and I know that they're on the 2 lines before the debug, and then I'm checking logic errors, which come after that. Once I've confirmed both of these, I don't need to look at this again. And then I continue to my next thing. So if a is equal to 4, we do something. Now, what we didn't do in this lab was actually check the conditions beforehand. Now, this is actually quite handy as well. So if I've got a condition, if a equals 4, I might put a debug inside here, but I'm more likely actually to put a debug here. So I'll put if def debug, end if, and I'm going to write printf, and I'll write debug, and then I'll write a equals 4. And what I will do is I will do a %d, then I will do a is %d. If I had more variables, I'd also do that as well. And then I will grab the conditional, so a equals 4, and then I will do the a. Okay. Now, then I compile, check my syntax, and then I can check my logic as well. So this is checking a couple of things. It's checking my variable, which is here, and it's also checking this a equals 4 does what I want. So if, for example, I accidentally had an equals here instead, I can see it very quickly. Okay, and then I can continue once I've confirmed that, that's done. Now I can do the code inside here. We did our debug inside, but it's generally better to do it before because then you get to actually check the conditional. Okay. Now, if you code this way using a simplified TDD, it pretty much means that your syntax and logic is flowing with the code. So once something works, it works. Okay. You can go back later and increase performance and increase efficiency, but it's generally the best practice to get your code working first, then increase efficiency and effectiveness. Okay? Does that make sense? Okay? I saw a lot of people adding the debug later, which just kind of, they didn't pick up many errors because they tested it so late that they didn't even know where they were, and they were fighting with syntax errors at the same time. So we did mention early on to compile every couple of lines, and this means that you can confirm syntax as you go. But now we have debug, so we can confirm syntax and logic at the same time. And we can put as much information in these debug information as we can. And when we have more complex conditionals, we can put a whole heap of information in here. So if I had, let's make this a little bit more complex, and you've got one in your assignment in a couple of places. So if I had quite a complex, and I might have multiple printfs in this case. So if I had if a equals 4 or a is less than 2, then my debug might actually have a couple of steps. And I might label the steps, so I might say something like this. So I might go a equals 4 or a less than 2, and then I'll put the results of that, and I might also include, actually I probably won't, so I might just leave it like that, and then put a new line, and then I'll put a equals 4 or a less than 2, and then I'll put printf, another D, and then I'll do a equals 4, so I check the left-hand side of that, do a %d, and then check that, and make sure that's working. Then I might check the other side, so the right-hand side of that, so I'll check the a less than 2, a less than 2, and I'll also check my a value. Okay, so you can see that I'm actually giving little snippets of code here. Now, the best way to do this is copy and paste. Now, the reason we use copy and paste here and not write it again is purely because you're testing your code. Now, there are better ways to do it than copy paste, and that's actually referring to the lines of code, but we haven't got that deep yet, so copy paste will do in this case. Okay, so we can see here that I've been able to fully make sure that the logic of this conditional works. Yes, 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 yes. 4 things work as I expect them to. And I can try a whole heap of different cases. Okay, does that make sense? So with your assignment, you can do the same thing and make sure that every step works. And on Friday's lab, I actually did this with the class because people came in really early. They were there at like 10:08, which was kind of good. So I went through the whole lab with them, and we got the lab done in half an hour because we were doing it this way. So we just got no errors when we got to the end because we were just checking. Does that make sense? So this is really helpful. And this is a development method. And if you go off and do other languages, there's a whole suite of tools for TDD. And if you want, you can have a read up on it. So, that's what TDD looks like. Okay. So it is testing as we go. Just write enough code. We recheck the tests. If it's successful, the test, then we keep updating and so on. Okay. All right. Cool, 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 cool. Super cool. All right. Now what I'm looking for. All right. Now, is there a particular topic, or was there something I said I was going to go back to? Oh, one other thing that I got asked today was this little dot here. Okay. And that's a fairly good question. So on an LMS, if you go to week 7, you've got all these flow diagrams. Now, flow diagrams are on the exam. Okay, I'm telling you that right now. Okay. Now, if you look at a do-while loop, you'll notice you'll see that little dot, and that gives you a clue that it's a do. Okay. And it tells you exactly that it's a do-while. Okay. So we can look at all these, and we can pick stuff up. So, for example, a for loop will always look something like this. We have an if statement. We have a while loop. And we have some examples in the early labs as well, with some of the ones given you. There's a really nice one this week, which is a triple for loop. All the symbols and what they mean. Now you'll also notice one other thing here, and this goes for the exam. I've lost you. Where did the peoples go? There's the peoples. With all of these, so for example, a do-while loop, you've got natural and code. So when you do a flow diagram, you can either do it naturally or you can do it as code. So here I've got declare input as an int, and here I've just got int input. Here I've just got the circle, here I've got do. Here I've got ask the user if they would like to continue. Here I've got printf continue question mark new line. Now it may be easier to do it this way or this way. It depends on what you prefer. Okay, and either way is suitable. Does that make sense? So you'll also notice that if you go on the exam tab, there's the flowcharts here as well. Okay. And you can see these came from. So that's a while loop. And so on. Okay. So know how to do those. They are quite handy. And also know how to do your box and pointer diagrams. All right. Also, if you started the assignment early, that's changed to a not. So just be aware of that as well. All right. All right. What else did I want to mention? Okay. Is there a particular topic that anyone would like to cover? Or would we like to have a look at a quiz, or would you like to cover a certain topic that people are struggling with? So you've submitted quiz book 11, haven't you? So actually do that. So we've got questions there. What is that looking? They're not going to be on the exam. So don't worry about that. Okay. So I might go and have a look at. Just trying to see if there's something that would be good. I think we've done most of the quiz questions. Right. So what I might do instead is open up let's do a cool question. All right, so this is a good question. It helps both with the exam and the assignment. All right, so I've got that question up on the screen. Make it a little bigger so we can read it. Might do that. Put it bigger here so it's clearer. Copy it across. That's kind of horrible to read. That's better. That's easier to read. All right. So have a go at that question, and we'll go through it. Okay. Have a look at some of the other questions. Cool. That's a difficult question. So have a try at that. It's not too difficult of a question, but it's a good start. Oh, and I've got a perfect question for Bitwise. After we do this question. So have a go. Even if you're not 100% sure, have a go. Have a guess of what you do. Just give everyone a chance. And if you're really not sure, say not sure. Try and have a go anyway. So I think most people got it. So we have two structs here, which is struct computer T. And then we have float price and int number of cores. So we have comp and comp2, and they both have two variables, one's price and one's number of cores. We set the price of the first one to 20.1. We set the number of cores to the first one to 2. We then, here, we have comp price plus 8.2. So comp price is going to be 20.1 plus 8.2. So we have 28.3. And we store that in comp2.price. So we get 28.2. And then here we have comp number of cores, which is 2. 2 times 2 is 4. So 4 gets stored into number of cores for comp2. And so we print 20.1. So we've got 0.1f. 2. There's no new line or anything. And we get 28.2 and 4. All right. So now I've got a better question. Okay. And this will test your bitwise blah blah. Let me just make it big. Oh, that's nice and big. Okay. How to go at this one? Now this one does require a bit of decimal conversion, but it's not very hard decimal conversion. So have a quick go at this. And then we'll go over to functions. Oh, these are good as well. How are we going? Are we winning? All right. So I'm just going to convert these to binary. So we have 0, 1, 5, and 2, 0, 0, 1, 0, if that helps. Obviously, there's going to be a whole heap of zeros after that as well, but we don't really care about that because we know that. So Z at the moment's nothing. So we've got X, which is 0, 1, 0. We've got Y, that's 0, 0, 1, 0. Now, Z becomes X shifted 2 places. So if we shift X 2 places, we get, so shifted, so 0, 1, 0, 1. Shifted 1 place is going to be 0, 0, 1, 0. Shifted 2 places is going to be 0, 0, 1. And you'll notice the shift is to the right. Okay, if it was a left shift, it would be going up. So Z now has 0, 0, 0, 1 in it. Then we have Y or Z. So we have 0, 0, 1, 0, or 0, 0, 0, 1. Now this is a bitwise OR. So a 0, 1, or 1, sorry, a 0 or a 1 will give a 1. A 1 or a 0 gives a 1. A 0 and a 0 gives a 0. And a 0 and a 0 gives a 0. And we know that the rest are zeros, so it just be zeros. So Z is now 0, 0, 1, 1. Then we have X becomes Y and Z. So we have Y, which is 0, 0, 0, 1, 0. Bitwise AND. Okay, so because it's singular, it's bitwise, not conditional. So 1 and 0 gives a 0. A 1 and a 1 gives a 1. And the rest is zeros. So X now has in it 0, 0, 1, 0. Y now has 1. So 1 is just 1. Shifted 2 places. So 1 place is going to be that. 2 places is going to be that. So Y has 0, 1, 0, 0. Now we just need to convert it back to decimal. So we have a 2, we have a 4, and we have a 3. So here we print 2, 4, 3. Does that make sense? So when I said earlier that you need to understand how the bitwise operations work, this is the kind of thing that you should understand. Okay. And an understanding like this may also help with the assignment, maybe. Most of it's in the operations though. But for the exam, definitely it's something that would be suitable. Okay. All right. So for the next question, actually we'll do a couple of quick questions and then I'll give you a longer question. And it's around structs, so it'll actually be helpful for the assignment as well. So for the longer question, I'm just going to give you a couple of quick questions. Zoom again. Okay, so I'm going to give you a couple of quick questions. Now there are worded questions in the exam, so be prepared to explain stuff. And these are quite good questions. Like there's one more that I liked. That one's no. Go away. Okay, so I've got 3 there. So there's something wrong with each one of these. Okay, so let's have a quick look. See if you can quickly just write down the answer or what you think is wrong for each one of these. Okay, so we all understand that index 10 exceeds the length of the array and hence is undefined. Further, dangerous. What about this one? Yep. So argument 2 in func call is of type int star star, whereas the parameter is expecting int star. Okay. Further, if we pass the address of this and the address of this, then X is going to hold basically an address which is not suitable. Okay, it's an int. So, well, not X. What X points to is an int. So we're going to change this to an address. Okay. Okay. What about this last one? Oops, I forget that question. if that's actually the case. Okay, so this one's quite a good one. So we have this X, which points to this location in memory, okay, which is a car. It's a single car, okay, which is perfectly fine. So we've just got a car in memory. It doesn't have a name. Sorry, I did that wrong. So we've got a single car in memory. It's just times by 1. And then I've got this other pointer, right? Now, I then change this to an A, the character A, and then I set Y to X. Okay. Then I free X. So this is now unallocated, okay? And so these both actually point to a null pointer. The same null pointer. Okay? And then I try and dereference this, but this memory is already freed, so we get a segfault. Okay? Hey, someone's joined us. All right. Does that make sense? So we can't free, if we've freed the memory, we'll get a segfault there because we're trying to deallocate, dereference to a null pointer. Oh, we're trying to print the null pointer as well. Yeah. All right. So, what we're going to do now is we're going to do a nice, easy exam question. And I'm going to give you a little bit of time for this one. And it's a really good one for both the practice for the exam and practice for the assignment. But I'm going to give you a little bit more time for this. So this should take 10 minutes max for an exam. Now, I'll just give you, no, we discussed nothing. I've just been quiet for the whole time. So I'll just give you some background. So this is a 10-point question, it should be 10 minutes. Now, with this question, in your exam, it's not just going to be a function, it's going to be a full program. So it will be worth a bit more and a bit longer than this. So it won't be this easy. But this one's fairly easy. So given this, I want you to write your function and then post it in the code. It should take less than 10 minutes, okay, if you're doing it in exam conditions. And considering you're doing structs right now, it shouldn't be too difficult. Okay, I'll be back in 5. Do the question. How are we going? We get in there? Give you a little bit longer. We'll go through it. And if you don't know, just say don't know at this stage. Now this should be. Why am I in grayscale? Considering your assignment is basically this, it shouldn't be too hard. And we'll do another version of this with a two-dimensional array. All right, I'll give you a couple more minutes. Just waiting a couple of answers. We'll keep going. Go through it. That's So if you got an answer, chuck down what you've got and start going through it. I think it's been over 10 minutes. Just chuck it in. I'll understand what you're doing. Just copy and paste. Doesn't have to be formatted. I can reformat it. So just chuck what you've got. Go through it. And then we can go through a two-dimensional, and it's pretty much the same thing as this. Except we're not using bits here. Alright. One ready. That. Two. So I'm going to copy those two across. The last person with this. Okay, so there's some good stuff in there, some bad stuff. So I'm going to go over the solution. All right. So we were at to start. So we're given the function prototype, so that makes it quite easy. It's void print large. What I might actually do before I start this is just make that smaller so I have a bit more room. Horrible. Oh. So I've got void print large houses struct house underscore t star h array int number of houses. Then I know that I need to iterate over these. So the first thing I'm going to introduce is I. Then I'm going to have a for loop. So I equals 0. I know the end of my for loop is less than none houses. And then I have I plus plus. In there, I want to go, so I'm going through all of them, okay, and there could be any amount. And I'm looking for ones with 4 or more bedrooms. So purely an if statement. If H array I dot non-bedrooms is it less than or which has 4 or more? Yep, so greater or equal to 4. Then we print it out. So printf house address equals it's a string such as, then there's a comma, then we've got price equals, we've got the dollars symbol, then we've got percent, point to F, and then we've got, let's just say new line, and then over here we'll have H array I dot address, and then H array I dot price, and that's done. Okay. So have a look at your solutions, and you can see you've got the print okay in most of them, but you forgot that it's a array, which in our assignment we're doing the exact same thing except it's a two-dimensional array. So don't forget that H array is an array. Yes, there is half marks. Well, no, there's not half marks, but the question will be marked out of 30 or something like that. Okay. So, for example, this question was worth 10. It might be for picking up the for loop and doing the for loop question, it might be 3. For doing this correctly, it might be another 3. For this, it might be 4. Something along them lines. And then the 4 out of that might be that you did this correctly, this correctly, this correctly, and this correctly. Okay. So going on that scheme, I don't have the average mark from last year. I can ask about that. I might actually do that. That's one thing I don't have right now. Okay. But for example, the solution that you gave, yes, so you'd probably get a 2 out of 10 for that solution because these were wrong, but the format specifiers were right. And you missed all that part. Or something along those lines. The weighting, I know it, but I'm not going to divulge it. All right. Now, because we've done the assignment, if I wanted to convert this to a two-dimensional array of houses, I could easily do this using the knowledge I've gained from doing the assignment. Because why are you doing this to me? So, oops, so I'm going to bring that down. I need a two-dimensional array, so oops. So if there's a two-dimensional array of houses, I can easily go to an array. Oh my God. So if there's then obviously I need a double star here. I'm going to introduce another variable called j, and I'm just going to have another for loop, which will be j equals 0. Now I'd also need to change the prototype, so num houses rows int num houses columns, which you're doing in your assignment, except for it's passed as part of the structure. So this might be rows, and then I'll have j. Now, how the rows and columns are set up depends on the matrix. it doesn't have to be this way. Now, I will generally always have y here, and x here, and z here, and z, that's an x, and move up in dimensions this way, but other people will go the other way. So you just got to be careful and have a look at the specs. So I've got that. Now I'm just going to move this across. And this is going to go really slowly. Again, why doesn't it move faster? That's really annoying. So I'm going to move that across, put that there or something. And now it's looking a lot more like our assignment. So it should be fairly easy at this stage because it's pretty much the same thing for some of this. Okay. And then all I need to change here is going to be, I now need another bracket, and same with here, maybe another bracket, and here. Okay, so now I can draw them in. My pen. What is it? Oh, I, J, I, J. Now it looks very similar to your assignment in terms of you've got a struct, which is two-dimensional. Okay. So that shouldn't be too difficult considering you've just done an assignment on it. Okay. You'll notice this too. So yeah, this is a lot simpler than would be on your exam, but there was more of these on this exam because this is just, it's not a full program, it's just a function where you'll do a full program. So maybe a couple of functions and main instead. But this is a reasonable question for 10%. Yours, I think, is worth 40%, or 30 or 40. I can't remember exactly. I'd have to have a look. I really can't be bothered right now. Sorry. All right, does that make sense? And does it make sense how I turned it into a two-dimensional? And if I wanted to change it into a three-dimensional, I just add another star, add int the z dimension, and then I add another for loop, and then I just add another bracket here, and I could just keep going. Okay. So this is all off the previous year's exams. Now, with the previous year's exams, they do look very different than this year's and last year's, and your practice exam that you'll do in a couple of weeks. Next week, sorry, not in a couple of weeks. However, they are still very good questions to practice of. Okay. However, some questions won't make sense. Okay, because we don't have that content anymore in the subject. So just be aware that. So, for example, here's a good example. So, a question like this, if it doesn't make sense to you, then it's not going to make sense because it's not taught anymore. So here's one. Please explain. I don't know why it says please on an exam. You should just say explain. You don't need to be polite. Explain what is the advantages and disadvantages of the fact processors have separate address spaces. Okay, so obviously that's not covered in this subject. We don't do processes, and we don't do threading. We don't do multi-threading, and we don't do IPC. When's the exam? 20th or something. Get the other guys to confirm that. The practice exam is next week, and you need to sign up for that on LMS. And you can attend 2 sessions. So I might just show you this. So all the previous years are there. Now, if you attend one of these practice sessions, you'll end up with a paper similar to this year's exam. That one will go up a little later, but not right now. So you'll notice that there's the Tuesday, and I recommend that you sign up for 2 if you can. So come on the Tuesday, and then come on another day as well, which would be Wednesday. Okay. Does that make sense? Is there any other questions that you would like to ask right now? The others are booked out. What do you mean the others are booked out? So Tuesday's still got 58 spaces, so you can come on Tuesday. And Wednesday's still got 15 places. Okay. So if you haven't chosen one, you can choose this Tuesday, or you can pick the other 2. Okay. Is there any other questions? Do we want to wrap up? I'm getting pretty tired. I think we might leave it there. Unless there's anything else you would like to discuss quickly. I don't understand what you're saying. Okay. Thank you for coming. I'm not allowed to divulge that information. Yeah, I'm going to cut that off.